A digital system built on ones and zeros cannot process an infinitely varying signal, such as the one shown in white. So instead, the system creates a list of the values by taking snapshots of the signal's value at regular intervals, as shown by the red markers on this graph. This interval is called sampling time. Another way to express this interval is in sampling frequency, which is the inverse of sampling time, and indicates the number of samples taken each second. From these samples, a signal may be reconstructed at a later time. However, if there is too much time between these samples, a phenomenon known as aliasing will occur. Because the samples in this figure are taken too far apart, the recreated signal, indicated by the red line, is created incorrectly. The most important thing we learned from this project is how and why the filter function works. The filter works by responding to specific rates of change in the input signal. If the signal fluctuates too fast or too slow, the signal gives little or no response to filtering it out. Recall that the order of filter we designed was 6. This number means that in addition to the newest input sample, the filter's equation uses 6 samples of the previous input and output values to calculate the next output value. On the figure here, the 6 stored values of the input are shown using blue markers, and the 6 stored values of the output are shown using red markers. With each new input sample, these stored values are used to calculate the next output value, as shown in the lower graph. After that, the stored values are shifted into the past. A new input sample is taken, and the process is repeated to calculate the next output. To process the input from a guitar, the signal will first be conditioned so that it utilizes the full range of the analog converter. Digital signal processors often have analog converters built into the chip. In either case, the signal is then processed through the filtering system. After that routine is complete, the signal is recreated by the digital converter and finally transmitted back to the amplifier. Initially, we had 2 digital signal processors that could be used to implement our system. Both were offered through Motorola. The first DSP package includes the evaluation board, debugging software, and code snippets, all for $75, while the second costs $950 for board and software, which are sold separately. The first DSP has great technical support through Freescale, while the second is no longer in production. Although the second DSP has significantly more capabilities, it has virtually no documentation. So the DSP model that we chose for our project is the CSM56F801 Evaluation Development Board. This particular model has a 16-bit processor with a 60 megahertz internal clock. It is equipped with several analog input channels and 11 general use input-output pins. A major drawback to this particular board is its lack of digital to analog converter to reconstruct the output signal. For this purpose, we employed a Maxim 16-bit digital to analog converter, shown here. This DAC supports a 3-wire serial data input, can handle a data clock rate of up to 10 megahertz, and can be powered by a 5-volt source. To condition the input signal from the guitar, we use 3 integrated circuit operational amplifiers. These op-amps come in 8-pin packages and require a 15-volt source. The input signal from an electric guitar typically stayed within a range of plus minus 0.3 volts, with occasional spikes up to 0.4 volts. However, the analog to digital converters on our DSP sample within a range of 0 to 3 volts. To utilize the full range of our DSP sampling capabilities, we use 3 operational amplifiers to scale and shift the input into the 0 to positive 3 volt region. The 3 op-amps are combined in the schematic below to shift and scale this input signal. The first op-amp buffers the signal by electrically isolating it from the guitar and the rest of the system. The second op-amp is configured as a summing amplifier, which scales and shifts the signal into a 3-volt range. However, this type of configuration places the signal into the negative range. So an inverting amplifier, the third one, is used to reflect the signal back into the positive region. Once the signal has been filtered within the DSP, it is output through the serial port and sent using a 3-wire serial connection to the digital to analog converter. In these 3 wires, the first is the clock, which 16 pulses are sent on the clock wire to tell the digital converter when to sample the data channel. Once all 16 bits have been loaded into the converter, a pulse is sent on the transmit done wire to begin the conversion process. Finally, the signal is rebuilt and sent to the amplifier. In our system, a button is used to switch between 2 modes, pass-through and filter. In either mode, the analog to digital converter samples the input repeatedly. And with each new sample, a subroutine is called. In pass-through mode, the input is sent directly to the serial port and then back to the amplifier. Whereas in filtering mode, the data is used to calculate the filter's response. Once the output is transmitted over the serial port, a short pulse is sent on the transmit done wire to begin the signal reconstruction in the digital converter. Testing revealed several flaws with our DSP system. The first problem concerns the limited amount of memory available in the DSP. Due to the complexity of our filter, we were only able to fit 1 filter function in the memory section allotted for user variables and code. Another obstacle was created by the data types used in our DSP. Over time, small rounding errors caused the system to behave unexpectedly. Occasionally, this resulted in overflow between the calculations and the filtering process. The most important problem we faced was diminished filter cycle frequency. The analog converter waits until the filter routine is complete before supplying the next input value. This extended processing time required for our algorithm caused the effective sampling frequency to plummet, which in turn caused aliasing. And finally, the response rails to the highest value. This slide shows potential solutions for each of these problems. To correct the memory problem, we consider methods to optimize the code through use of circular buffers and pointers rather than memory arrays. Another option would be to use the programming language assembly code rather than C. Assembly code is a set of instructions that directly corresponds to the machine code of the DSP. Another way to optimize a program would be to use a different filtering approach, which reduces the number of saved samples needed by combining the input and output arrays into one array. To handle the accuracy problem, the filtered data may be scaled to prevent overflow between the calculations of the filtering routine. To fix the third problem, a more efficient DSP instructions may be used to ensure processing speed. Late in the project, we discovered a pre-written filter function in the DSP's source code. However, this function required that our filter be broken up into smaller sections and then cascaded as a multi-stage filter.
The materials needed for a final product version of this project are listed in this table. 3 op amps would be needed to modify the input signal as previously described. Assorted resistors would be needed to control the gain in the op amp train. A digital to analog converter would be needed to output the signal from the DSP to an amplifier. 4 green LEDs would be needed to keep track of the key number of the filters. A red LED would be needed to indicate if the power of the device is on or off. 2 push button switches would be needed, one for turning the power on and off, and the other for changing the key. 2 1/4-inch female jacks would be needed to input and output the signal. A 5 volt to plus minus 15 volt DC voltage converter would be needed to provide voltage to the op amp train. A 2-inch by 3-inch solder board would be needed to make all the necessary connections to and from the DSP. Some sort of housing would be needed to protect the device while it is in use. The DSP module would be needed to run the filtering process. The total cost for each device comes out to be $138.85. Mass production would cut these costs considerably since materials are cheaper when bought in bulk. Also, the costs for designing the product and labor would be distributed with each unit, drastically lowering these costs.